In 1844, a French mathematician proved that almost every number on the line you were shown as a child has no name, no equation, and no possible description. It was correct. It was checked. But the field kept the clever part, shelved the meaning, and went quiet about what it actually proved, that the numbers you can name are a vanishing accident floating on an ocean of numbers no person and no machine will ever be able to speak. That should have rewritten how you picture reality. Instead, it became a homework exercise. Tonight, you follow that buried result all the way to the bottom. Through Cantor, who proved the unnameable numbers are almost all of them, and was called a corrupter of youth before he died in a sanatorium. Through a constant called gamma that runs all through physics, and that nobody to this day can prove is even a simple fraction. Through Turing, and a single number whose every digit hides a question no machine can answer. And finally to 1963, when two proofs together showed we cannot even decide how many numbers the line contains. So get comfortable. If you are new here, subscribe or join so the next one finds you. And the wider trails, the ones across physics and math and deep time and the ways things fall apart, live over on the Patreon. Stay to the end, because by then, the line under everything you have ever measured is going to look less like a ruler and more like a held breath. Let's go back to where this began. Somewhere between 0 and 1, on the number line you have known your whole life, there is a number that will never be named. Not by you, not by anyone, not by any person who has ever lived or ever will, not by any machine we have built or could ever build, not in a billion years of trying, not in the entire remaining lifespan of the universe. It is sitting there right now, a perfectly real point on a perfectly ordinary line, and it has no name, and it never will. And here is the thing I need you to hold on to before we go one step further, because everything that follows depends on it. That number is not the strange one. That number is the rule. That kind of number is almost all of them. Take the line you were shown as a child. 0 in the middle, the numbers marching off in both directions, neat little tick marks at every whole step. Forget the negatives for now. Forget everything past 1. Just take that one small stretch between 0 and 1, that single finger width of the line, and imagine throwing a dart at it. Not a real dart, an idealized one, infinitely sharp. Landing on exactly one point, with infinite precision, you throw it. It lands. And the number it lands on, with a probability that is not close to 100% but is exactly 100%, is a number that can never be written down, never be calculated, never be described by any finite rule, and never be given a name. You will have pointed at it. You will never be able to say what it is. That is not poetry. That is not a metaphor for how big infinity is. That is a theorem. It was proven, in stages, by men who were called frauds and madmen for proving it, and once it was proven, the world quietly looked away from what it meant, and has been looking away ever since. The first crack in the door opened in 1844, and what came pouring through that door over the next 90 years was so much worse than the thing that opened it, that the man who opened it never lived to see how far down it went. You were given a version of numbers that is clean. Counting. Fractions. The square root of 2, pi if your teacher was feeling ambitious. That version is not wrong. It is a postage stamp laid on the surface of an ocean, and you were told the postage stamp was the ocean. The numbers you can name, all of them, every number that has ever appeared in a textbook or an equation or a calculator, every number that will ever be printed or spoken or stored, all of them together form a set so vanishingly thin compared to the whole line that if you picked a number at random, you would never, not once, not in infinite tries, land on one of them. The nameable numbers have a measure of 0. They take up no room. They are the exceptions. And almost everything else, the actual body of the number line, the thing that is really there underneath your dart, is a kind of number we proved exists, proved is overwhelming, and still to this day can barely point to. They are called transcendental numbers, and the story of how we found out they are almost everything, while remaining almost entirely unable to name a single one of them, is the most unsettling thing I have ever read in mathematics. I want to walk you all the way down it. Because it does not end where you think it ends, with pi and a shrug. It keeps going. It goes past numbers we cannot name into numbers no machine can compute, and then past those into numbers that cannot even be described. And then it arrives somewhere I genuinely did not expect. A place where mathematics turns to its own foundations and asks a simple question: how many of these numbers are there? And the foundations answer back that the question has no answer and never will. We will get there, but you need to start at the door, because the man who opened it did it almost by accident, and what he was actually trying to do was win an argument. His name was Joseph Liouville. He was born in the town of Saint-Omer in the north of France in the spring of 1809, and by the time he was in his 30s, he was one of the most quietly powerful mathematicians in Paris. Not because of any single famous result, but because he ran the room. In 1836, he founded a journal, the Journal de Mathématiques Pures et Appliquées, which people simply called Liouville's Journal, and it is still one of the leading mathematics journals on Earth almost 2 centuries later. If you wanted your work read in France, it went through him. He held the chair at the Collège de France. He sat at the centre of French mathematics like a spider at the centre of a web. And that detail matters, because the thing he is about to prove is going to be ignored for 30 years, even though the most connected man in the field is the one who proved it. But I want to tell you something about Liouville before we get to the mathematics, because it tells you what kind of man he was, and it will come back at the very end of this, in a way I did not expect when I started reading about him. In the 1830s, a young man named Évariste Galois had died in a duel at the age of 20, having scribbled down, the night before he was shot, a theory so far ahead of its time that nobody who read it could understand it. His papers sat in a drawer, dismissed for years. They were the work of one of the great geniuses in the history of mathematics, and they were treated as the ravings of a hot-headed boy. And it was Liouville, starting around 1842, who sat down with those rejected papers, recognized what they were, filled in the gaps, and announced to the Academy of Sciences that this dead 20-year-old had been right about everything. He published Galois in his journal in 1846, 14 years after the duel. He spent his own time and his own reputation rescuing a name from silence. Hold that. A man who built a career on the certainty that numbers behave, who believed in order and structure, spent his evenings dragging a forgotten genius back out of the dark, because the thing he is about to discover is that the number line is mostly silence, mostly names that will never be recovered. And he, of all people, was the one who first proved how much of reality is permanently lost. The personal and the mathematical are not two separate stories here. They almost never are. So here is what Liouville was actually doing in 1844. He was not hunting for monsters. He was trying to settle a question that had been hanging in the air for almost a century. A question that sounds simple and is not. Are there numbers that are not the solution to any equation? Let me be precise, because this is the hinge the whole thing turns on. And if you get this, you get everything that follows. You know what an equation is. Something like x squared minus 2 equals 0. The answer to that one is the square root of 2, an ugly endless decimal, 1.414 and so on forever, with no repeating pattern. The square root of 2 is irrational. You probably learned that, and you were probably left with the impression that irrational is the bottom, that once a number's decimals go on forever without repeating, you have reached the wild frontier of numbers and there is nothing stranger past it. That impression is wrong, and correcting it is the first thing I need you to let go of, because almost everyone carries it, and it is the exact misunderstanding that hides the real story. The square root of 2 is irrational, yes, but it is also tame in a way that matters enormously. It is the solution to that equation, x squared minus 2 equals 0. It is an answer to a question you can write down with whole numbers. Mathematicians call numbers like that algebraic. The whole numbers are algebraic. The fractions are algebraic. The square root of 2 is algebraic. The cube root of 7, the golden ratio, any number you can trap as the root of a polynomial with ordinary integer coefficients, all algebraic. These are the numbers that answer to us. They are the solutions to equations, and equations are the closest thing mathematics has to a leash. An algebraic number is a number you can summon by writing down its equation. It might have an infinite messy decimal, but it has a finite address. You can point to it and say, "You, the number that does this." A transcendental number is a number with no equation. No polynomial with whole number coefficients has it as a root. Not a quadratic, not a cubic, not a degree 1000 monster, nothing. It transcends algebra entirely, which is where the name comes from. Leibniz coined the word transcendental for exactly this idea, a quantity that climbs above the reach of algebraic methods. And for over 100 years after the idea was named, nobody could prove that a single such number existed. People suspected. Euler suspected. Everyone had a feeling that pi and e were somehow lawless in this way. But suspicion is not proof, and the question sat there, open, embarrassing, unanswerable. Did these lawless numbers actually exist? Or was every number, given enough cleverness, secretly the answer to some equation we just had not found yet? And here is where Liouville does something I find genuinely beautiful, because he does not go looking for a number that already exists, like pi, and try to prove it is transcendental. That problem was too hard, and he knew it was too hard. Instead, he asks a different and sneakier question. What would a transcendental number have to behave like? If such a number existed, what would be true of it that is not true of the tame algebraic ones? And he found an answer, and the answer is about how well a number can be approximated by fractions. This is the part where I have to ask you to slow down with me, because it is the engine of the whole proof, and it is not hard. It is just unfamiliar. Every number you can sneak up on with fractions. Pi is roughly 22/7. It is more precisely 355 over 113. You can get closer and closer to any number using fractions with bigger and bigger bottoms. The question Liouville asked is, how fast? How good an approximation do you get for how big a denominator? And he proved something restrictive about the tame numbers, the algebraic ones. He proved that an algebraic number, if it is irrational, actually resists being approximated too well. There is a limit to how tightly fractions can hug it relative to the size of their denominators. An algebraic number of a given complexity keeps fractions at arm's length. It will let them get close, but not too close too cheaply. This is now called Liouville's theorem, or Liouville's inequality, and the precise statement is that for an algebraic number of degree n, no fraction of a q can come closer to it than roughly 1 over q to the power n. The denominator buys you accuracy, but only at a fixed exchange rate, set by the number's own complexity. Sit with what that gives him. He now has a fingerprint. He has a property that every algebraic number must obey. Algebraic numbers cannot be approximated too well by simple fractions. So if he can build a number that can be approximated absurdly well, a number that lets fractions hug it impossibly tight, far tighter than Liouville's theorem ever allows for an algebraic number, then that number cannot be algebraic. It cannot be the solution to any equation. It would have to be transcendental. He would have caught one, not by finding it in the wild, but by constructing it to violate the law that all tame numbers obey. And so he builds one. And the number he builds is so simple that it almost feels like cheating, except it is not cheating, it is airtight. Take a decimal point, then put a 1 in the first place after it, then a 1 in the second place, then zeros, 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 until you reach the 6th place, and put a 1 there. Then zeros again, a long run of them, until the 24th place, and put a 1 there. Then zeros until the 120th place, another one. The ones land only at positions that are factorials: 1, 2, 6, 24, 120, 720, the numbers you get from multiplying 1 times 2 times 3 and on up. Everywhere else, 0. It is a sparse, lonely scattering of ones in an endless field of zeros, with the gaps between the ones growing explosively, brutally fast. That number is now called the Liouville constant. It begins 0.110001, and then a yawning desert of zeros before the next one appears. And because the gaps between the ones grow so fast, the number can be approximated by simple fractions with shocking, illegal precision. Each time you chop it off at the next one, you get a fraction that hugs the true value more tightly than Liouville's theorem permits for any algebraic number of any degree. It is too well approximated to be tame, therefore it has no equation, therefore it is transcendental. And in 1844, in 2 short notes to the Paris Academy, Joseph Liouville became the first human being in history to hold up a specific number and prove, with certainty, that it answers to no equation that will ever be written. It should have been an earthquake. A century-old question, answered, the first proof that the lawless numbers are real, and the response was, more or less, polite interest, and then silence. Because here is the thing about Liouville's number, the thing that makes it feel like a magic trick rather than a discovery. He built it on purpose to be transcendental. He engineered it. It does not occur in nature, it does not fall out of geometry or analysis, it is not pi or e, it is a number assembled in a workshop specifically to break a rule. And so the mathematical world looked at it and thought, fine, you have shown that if you carefully manufacture a freak, the freak is transcendental. But who cares about freaks? The real numbers, the ones that matter, pi and e and the constants that show up when you actually do physics, those are surely still algebraic, or if not, surely transcendental numbers are some rare exotic species you have to build by hand. A curiosity, a footnote. Every single piece of that assumption was about to be proven wrong, and not by a little. The transcendental numbers are not a rare exotic species. The freak Liouville built by hand is not the exception. It is one of the only members of the family we will ever be able to name, precisely because we built it. The wild ones, the ones we did not build, are almost all of reality, and we cannot get to them. But nobody knew that yet in 1844. The door was open. Liouville had proven the lawless numbers exist. What he had not done, what he could not have imagined, was that 30 years later, a younger, stranger, far more tormented man was going to walk up to that same door, look through it, and count what was on the other side. And the counting was going to break him. But before we get to him, I want to name the thing Liouville did not do, because it is going to haunt this entire story. He proved that transcendental numbers exist. He did not, and could not, prove that any number you actually cared about was one of them. Pi remained unproven. E remained unproven. The most important constants in mathematics sat there, suspected of being lawless, and nobody could close the case. That gap between knowing the lawless numbers are real and being able to point at a real one opened in 1844, and it has never fully closed. It is open right now. There are numbers on your calculator, numbers you have typed 100 times, that we still cannot prove are transcendental. We will get to them, and when we do, I think you are going to feel the same thing I felt, which is something close to vertigo, because the gap is not closing. In a sense we are about to make precise, the gap is the entire point. Liouville opened a door onto a room, and the first thing the next man through that door discovered was that the room had no walls and no floor, and that we were already falling. His name was Georg Cantor, and almost nothing about how his life ended makes sense until you understand what he found. Cantor was born in St. Petersburg in 1845, the year after Liouville opened the door, which is a coincidence, but a tidy one. His family moved to Germany when he was a boy. He was a gifted violinist, a serious religious man, and by his late 20s, he was a professor at the University of Halle, a respectable but second-tier institution, a fact that is going to matter, because Cantor spent his whole life desperate to get to Berlin, the real centre of German mathematics, and he was never allowed in. The man who kept the gate at Berlin was named Leopold Kronecker, and Kronecker is going to become the villain of this story, though I want to be careful with that word, because what he did was not cartoonish villainy. It was something more recognisable and more damning. He could not tolerate an idea, so he tried to destroy the man who had it. In 1874, Cantor published a paper in Krell's journal with a title so dry it gives away nothing, on a property of the collection of all real algebraic numbers. Read that title again and notice what it is about. The algebraic numbers. The tame ones. The ones that answer to equations. Cantor was asking a question that on its surface sounds almost clerical. How many algebraic numbers are there? And the answer he gave is the moment infinity stopped being a single vague idea and became a hierarchy of monsters. Here is what he proved, and I am going to build it carefully, because this is one of those arguments where the moment it clicks, something in your understanding of size permanently rearranges itself. We are used to the idea that there are infinitely many whole numbers, 1, 2, 3, and so on forever. That infinity, the infinity of the counting numbers, Cantor gave a name. He called it countable. A set is countable if you can, in principle, line its members up in a list, a first, a second, a third, such that every single member eventually appears somewhere on the list, even if the list never ends. The whole numbers are obviously countable. They come pre-listed. The interesting part is what else turns out to be countable, because the answer is far more than you would think. The fractions are countable. That already feels wrong, because between any two fractions there are infinitely many more fractions. They are packed in densely with no gaps you can see. And yet Cantor showed you can arrange every fraction that exists into a single endless list with none left out. The trick is to organise them in a grid and snake through it diagonally, and once you do, every fraction gets a position, a first, a second, a thousandth. Infinitely many of them, but countable. Lineable. And then Cantor pushed harder, and here is the result that title is hiding. The algebraic numbers, all of them. Every solution to every polynomial equation with whole number coefficients. The square root of 2, and the cube root of 7, and the golden ratio, and every other tame number in existence. All of them. are also countable. You can put every number that answers to an equation into one endless list. They look like they should be vastly more numerous than the whole numbers, and they are not. They are the same size of infinity. Countable. I need to pause on how strange that already is before Cantor delivers the blow, because if you do not feel the strangeness here, you will not feel the floor drop in a moment. Every equation you could ever write, every solution to every one of them, all the algebraic numbers fit into a list no longer than the list of plain counting numbers. They are tame not just individually but collectively. They can be enumerated. Reality, if it were made only of algebraic numbers, would be a thing you could in principle read off item by item forever and never miss one. I want to make that word, countable, feel like something, because it is easy to let it slide past as jargon, and the whole story depends on feeling the difference between countable and uncountable in your gut. Countable means listable. It means that no matter how enormous and dense the set is, you can in principle assign its members to positions on an infinite ticket line. Member number 1, member number 2, member number 3, going on forever, and every single member eventually gets a ticket. The fractions are countable, which already strains belief, because between any two fractions you care to name there are infinitely many others, packed in with no visible gaps, and still, somehow, you can put all of them in a single line with each one getting a definite position. The algebraic numbers are countable. Every solution to every polynomial equation that will ever be written, all of them, fit on one infinite ticket line. That is an unimaginably vast collection, and it is still, in Cantor's precise sense, the smallest kind of infinity there is. Uncountable means there is no ticket line. It means that no matter how you try to assign positions, no matter how clever your scheme, you will always, provably, leave almost everything out. Not a few things, almost everything. The reals are uncountable, and the gap between countable and uncountable is not like the gap between 1,000 and 1,000,000, or even between 1,000,000 and 1,000,000,000. Those are differences of degree, all of them sitting comfortably inside the finite. The gap between countable and uncountable is a difference of kind, a wall, a place where one sort of infinity ends and a strictly larger sort begins. And the diagonal argument is the proof that the wall is real, and that no listing scheme whatsoever can ever climb over it. And now, the measure, the thing that turns the dart from a metaphor into a theorem. Take the algebraic numbers, all of them, that vast countable collection, every root of every equation. Because they are countable, you can do the following, and the fact that you can do it is genuinely staggering. Line them up. First, second, third. Around the first one, draw a tiny interval of length 1/2. Around the second, an interval of length 1/4. Around the third, 1/8, and so on, halving each time. You have now covered every single algebraic number with its own little interval. Every root of every equation is sitting inside one of your intervals. And the total length of all those intervals added together, 1/2 plus 1/4 plus 1/8 and on forever, comes to exactly 1. You could start the interval smaller, with length summing to 1,000th or 1,000,000th, or any tiny number you choose, and still cover every algebraic number that exists. The entire infinite collection of solutions to all equations can be hidden inside a set of intervals whose total length is as close to nothing as you like. That is what measure zero means. It is not a figure of speech. The algebraic numbers, all of them, genuinely take up no length on the line. You can sweep the whole infinity of them under a rug smaller than a grain of sand, and what is left over, the part with the full length, the part your dart almost certainly lands on, is the transcendental ocean, untouched by the rug, occupying the entire line. And then Cantor asks the obvious next question. What about all the real numbers? Not just the algebraic ones, but the whole line. Every point on it. Can you list those too? And he proves, in a few lines that are still taught to every mathematics student on Earth, that you cannot. The real numbers are not countable. There is no list, no possible list, no infinitely long enumeration of any kind that contains all of them. You cannot line them up. The infinity of the real line is a strictly, provably larger infinity than the infinity of the counting numbers. It is a bigger size of forever. His 1874 argument did this with a clever nested interval construction, but 17 years later, in 1891, he found the cleaner version, the one that has become one of the most famous arguments in all of mathematics. And it is so simple I can give it to you in a breath. Suppose someone hands you a list claiming to contain every number between 0 and 1, a first number, a second, a third, on forever. You build a new number like this. For its first decimal digit, you look at the first digit of the first number on the list, and you choose something different. For its second digit, you look at the second digit of the second number, and choose something different. Down the diagonal you go, disagreeing with the list at every step. The number you build differs from the first number in the first place, from the second in the second place, from the nth number in the nth place. It cannot be anywhere on the list, because it differs from every entry in at least one digit. You have built a real number that the list missed. And you can do this to any list. Always. No list can ever be complete. The reals cannot be counted. That argument is called Cantor's diagonal argument, and it is the same weapon, the exact same move, that is going to come back 3 more times in this story. Each time to prove that some new category of numbers is too vast to reach. Remember the diagonal. We are going to use it to kill computers and to kill language itself before we are done. Now put the 2 results side by side, because this is the whole thing. This is 1874 in one sentence. The algebraic numbers are countable. The real numbers are not. And the transcendental numbers are just the real numbers with the algebraic ones removed. So if you take an uncountable infinity, the reals, and remove from it a merely countable infinity, the algebraic numbers, what is left is still uncountable. It has to be. A countable set cannot fill an uncountable one. Which means the transcendental numbers, the lawless ones, the ones Liouville had to build by hand 30 years earlier because he could not find one in the wild, are not rare. They are not exotic. They are not a species you have to manufacture. They are almost the entire number line. The tame algebraic numbers, all of them, are the thin scattering. The transcendental numbers are the ocean. Liouville thought he had caught a rare fish. Cantor proved that the rare thing, the freakish exception, was the dry land. And here is the version of that fact that I cannot stop thinking about, because it is the version that has teeth. Cantor's proof tells you the transcendental numbers vastly outnumber the algebraic ones, but it does something worse than that, something almost cruel, and to feel it you have to go back to the dart. There is a way of measuring sets of numbers, a notion of size that is not about counting, but about how much room a set takes up on the line, and it is called measure. The whole stretch from 0 to 1 has measure 1, the full length, and it is a theorem that any countable set of points, no matter how densely it is sprinkled along the line, has measure 0. It takes up no length at all. You can cover the entire infinity of algebraic numbers with a collection of tiny intervals whose total length is as small as you like, smaller than a millionth, smaller than a billionth, as close to nothing as you want. The algebraic numbers, every solution to every equation, occupy literally 0% of the number line, which means the dart. Throw your infinitely sharp dart at the line between 0 and 1. the probability it lands on an algebraic number, a number that answers to any equation, a number you could in principle summon by writing its polynomial, is 0. Not small. 0, and the probability it lands on a transcendental number is 1. Certainty. Every time, forever. If you threw that dart once a second for the entire age of the universe, and then for 1 trillion universes after that, you would never once land on a number that has an equation. You would land every single time on a lawless number. And as we are about to see, naming even one of the numbers you landed on would in most cases be beyond not just you, but beyond the combined effort of every mathematician who will ever live. You would be pointing, with certainty, at something that cannot be spoken. That is the reopened file, and I want to make sure you feel how it reopens. You were taught the number line as a friendly thing, populated by the numbers you know, with a few irrational oddballs thrown in. The truth is the reverse. The numbers you know are the oddballs. The line is made of the unspeakable, and the speakable numbers are a measure zero accident floating on top of it. And you were never told. And the reason you were never told is the same reason the man who proved it died where he died, because Kronecker could not stand it. Leopold Kronecker was a brilliant mathematician and a powerful one, and he had a philosophical commitment that hardened, over the years, into something like a religion. He believed that mathematics should be built only out of the whole numbers and finite steps. He has a famous line delivered at a meeting in 1886. God made the integers, all the rest is the work of man. He meant it as a boundary. The whole numbers are real and God-given. Everything else, the irrationals, the infinities, the actually existing transcendental ocean Cantor was describing, all of that was, to Kronecker, human invention at best and dangerous nonsense at worst. And Cantor was not just using infinity, he was proving there were different sizes of it, building a tower of infinities each larger than the last, treating the uncountable as a real and completed thing. To Kronecker this was not bold mathematics. It was a kind of heresy, and he set out to stop it. He did not stop it with a counter-argument, because there was no counter-argument. The proofs were correct. They are still correct. Instead, he used the thing he actually had, which was power. As an editor and a gatekeeper, he delayed Cantor's publications. As the dominant figure at Berlin, he made sure Cantor would never get the position there that he desperately wanted, leaving him stranded at Halle for his entire career. And he attacked Cantor personally, in private and in public, in terms that are still shocking to read. He called him a charlatan. He called him a renegade, and most memorably, he called Cantor a corrupter of youth, the same phrase, almost word for word, that was used to condemn Socrates to death. A phrase that accuses a man not of being wrong, but of being a kind of moral poison to the people around him. Henri Poincaré, one of the greatest mathematicians of the age, looked at Cantor's set theory and called it a grave disease, a perverse pathological illness that mathematics would one day need to be cured of. Think about what that does to a person. You have proven something true, not arguable, true, with a proof anyone can check and no one can break. And the most powerful people in your field respond not by checking the proof which would vindicate you, but by calling you sick, calling you a corrupter, treating the truth you found as a contagion to be quarantined. The mechanism here is the thing I keep coming back to in this whole subject, because it is not a conspiracy, and it is not even really about mathematics. It is about comfort. The result was too uncomfortable to absorb, so the establishment did not refute it. It pathologized it, and the man who carried the result paid for it with his mind. Cantor's first serious breakdown came in 1884, when he was 39. He spent time in a sanatorium. He recovered and relapsed and recovered and relapsed, for the rest of his life, the depressions coming more frequently and lasting longer as the years went on. There is a temptation to draw a clean line from Kronecker's persecution to Cantor's illness, and that is too simple. Mental illness does not work like a morality play. He very likely would have suffered regardless. But it is also too simple to pretend the two had nothing to do with each other. He was a man holding a true and enormous thing, being told by the people he most respected that holding it made him diseased, and the holding got harder every year. And here is the detail I promised would come back, the one I need you to file away now, because it pays off at the very bottom of this descent. Cantor was deeply, seriously religious, and he did not experience his infinities as cold mathematics. He experienced them as theology. He drew a distinction, in his own writing, between two kinds of infinity. There was the transfinite, the actually existing mathematical infinities he had discovered, the countable and the uncountable, and the tower above them, which were created things, part of the world, available to mathematics. And then there was something he placed beyond all of them, which he called the absolute infinite, and which he identified with God. The absolute was not a number, not even a transfinite one. It was the unreachable thing above the entire tower, beyond mathematics, beyond comprehension, where the hierarchy of infinities pointed, but could never arrive. Cantor believed his mathematics was a way of glimpsing the structure of the divine. He was not being metaphorical. He corresponded with Catholic theologians about it. He thought he was doing God's work, mapping the lower floors of a tower whose top was God himself. And there was one question, one specific mathematical question, that he became convinced was the key to the whole structure, and that he could not answer no matter how hard he tried for the rest of his life. He had proven the reals were a bigger infinity than the counting numbers. The natural next question was, is there anything in between? Is there a size of infinity strictly larger than the countable whole numbers, but strictly smaller than the uncountable reals? Or does the line jump straight from one to the other with nothing between? Cantor was certain the answer was no, that there was nothing in between, that the reals were the very next size of infinity after the countable. This belief is called the Continuum hypothesis. He tried to prove it for decades. He thought he had proven it, then found the error. He thought he had disproven it, then found that error too. It consumed him. He believed God knew the answer, and that he, Cantor, had been chosen to find it, and he never did. I am telling you about the Continuum hypothesis now, this early, because I need you to carry it with you all the way down. The question of whether there is a size of infinity between the integers and the reals is going to turn out to be the floor of this entire descent, the very bottom. And what happens to that question in the year 1963 is the single most disorienting thing in this story. Cantor died believing it was a question that God could answer, and that he had failed to. He was wrong about the second part. It was not that he failed. We are going to find out, decades after his death, that the question he spent his life on cannot be answered at all. Not by him. Not by us. Not by any mathematician who will ever live. Not because we are not clever enough, but because the foundations of mathematics themselves are silent on it. The thing he thought only God could decide turned out to be a thing that nothing can decide. But that is the bottom of the staircase, and we are still near the top. Cantor's son Rudolf died in December of 1899, and something in Cantor seemed to break further after that and not come back. He kept working, kept teaching, kept relapsing into the sanatorium at Halle. He retired in 1913. During the First World War, he lived in poverty and, by some accounts, hunger in a Germany that was starving. He spent the last year of his life in the sanatorium, and he died there of a heart attack on the 6th of January 1918. The man who proved that the numbers we cannot name make up almost all of reality spent his final years in a place built to contain minds that could no longer be reached, which is the kind of irony that this subject keeps producing. As if the mathematics insists on writing itself into the lives of the people who touch it. His infinities won, by the way. Completely. David Hilbert, the most respected mathematician of the next generation, said that no one would ever expel mathematicians from the paradise Cantor had created. Today, every mathematics student learns the diagonal argument, learns that the reals are uncountable, learns that the transcendental numbers are almost all of them, usually in their first or second year, often without ever being told what it cost the man who found it, or what it actually means about the dart and the line. The result was absorbed. The unsettling part was filed away. And the specific, practical, infuriating consequence of all of it, the consequence Cantor's proof guarantees but does not resolve, was left for the rest of us to choke on. Because Cantor proved the transcendental numbers are almost everything, he proved that if you reach into the line you will, with certainty, pull out a lawless number. But his proof is what mathematicians call non-constructive. It tells you the ocean is there. It does not hand you a single drop. The diagonal argument proves a list of reals must be incomplete, but the number it builds depends on the list. It is not a specific famous constant. It is a freak assembled to defeat one enumeration, the same flavour of manufactured oddity as Liouville's. Cantor told us with total certainty that almost every number is transcendental. And then, when you ask him the obvious question, all right, show me one that I actually care about, show me that pi is one of them, his proof goes quiet. It cannot. It was never about any particular number. It was about all of them at once. And at the level of all of them at once, the answer is overwhelming and clear. And at the level of any single one, the answer is, prove it yourself. That was the state of things by the 1870s. We knew the lawless numbers were almost everything. We had two examples, both built by hand, Liouville's constant and the freaks the diagonal argument spits out. And we still could not prove that any number a normal person had ever heard of was transcendental. Pi was unproven. E was unproven. The two most important numbers in mathematics, the ones that show up everywhere from the area of a circle to the growth of populations to the behaviour of waves, sat there under suspicion, almost certainly lawless, and no one could close the case. The ocean was proven. Naming even one specific wave in it was, somehow, still beyond us. And the man who finally named the first one, who reached into the water and pulled out a number everyone actually cared about and proved it was lawless, did it for the number E, and then he looked at pi, the obvious next target, the one the whole world wanted, and he flinched. He wrote a letter saying he would not even try. He said it would cost whoever attempted it dearly. And he was right. His name was Charles Hermite, and he was, by the accounts of everyone who knew him, one of the kindest men in the history of mathematics. Which is worth saying because this story is so full of cruelty that the gentle ones stand out. Hermite was born in Lorraine in 1822 with a deformity in his right foot that left him walking with a cane his whole life, and that, in a grim bit of luck, kept him out of military careers and pushed him toward mathematics. He was a terrible test taker. He nearly failed out of the École Polytechnique, the most prestigious scientific school in France, because he could not perform on examinations, and he spent a good part of his career without the credentials his talent deserved. But he had a gift for seeing the hidden machinery of numbers, and in 1873 he pointed that gift at the number E. You know E even if you do not think you do. It is the number, roughly 2.718, that governs anything that grows in proportion to its own size. Compound interest, bacterial growth, radioactive decay, the cooling of your coffee. It is woven into the deep structure of calculus so thoroughly that you cannot do serious mathematics without it. and in 1873 Hermite proved that E is transcendental. It is not the answer to any equation. It is lawless. And crucially, unlike Liouville's constant, E was not built to be lawless. It is a natural object, the most natural object, falling out of the basic structure of growth and change, and Hermite proved that this utterly fundamental number, this number at the heart of all of analysis, has no algebraic address. It transcends. It was the first time anyone had taken a number that already mattered, a number nobody manufactured, and proven it was one of Cantor's ocean. The proof was hard. It was the kind of hard that leaves a person depleted, and when it was done, everyone in the mathematical world immediately thought the same thing, the thing you are probably thinking right now. If E is transcendental, what about pi? Pi was the bigger prize. Pi carried 2,000 years of history on its back, because hiding behind the question of whether pi is transcendental was one of the oldest unsolved problems in all of mathematics. The problem of squaring the circle, and I will explain why those two questions are secretly the same question in a moment. The point is that pi was the trophy. Everyone wanted it. And Hermite, the one man on Earth best positioned to go after it, having just built the machinery that could plausibly do it, refused. He wrote a letter, and the line from it has survived because it is so honest, it almost hurts. He wrote, "I shall not risk anything on an attempt to prove the transcendence of the number pi. If others undertake this enterprise, no one will be happier than I at their success, but believe me, my dear friend, it will not fail to cost them some effort." Read that again and hear what it actually is. It is a brilliant man, holding the exact tools that could win the most famous prize in his field, looking at the prize and saying, "Not me, it will cost too much." He had just paid the price for E, and he knew what the price for pi would be, and he declined to pay it. There is no shame in it. There is something almost wise in it. But it left the door open for someone else, someone younger and hungrier, and willing to spend what Hermite would not. That someone was Ferdinand von Lindemann, a German mathematician born in 1852. And in 1882, 9 years after Hermite cracked E, Lindemann took Hermite's machinery, extended it with one crucial new idea, and proved that pi is transcendental. The paper was called simply Über die Zahl Pi, on the number pi, and it appeared in the Mathematische Annalen. And with it, a problem that had been open since antiquity, since before Euclid, closed forever. Here is why this was not just one more transcendental number, why it rang bells across the entire mathematical world in a way E had not quite managed. Squaring the circle is the ancient challenge of constructing, using only a compass and an unmarked straightage, a square with exactly the same area as a given circle. The Greeks tried. Everyone tried. For more than 2,000 years people attempted it, and it became a byword for an impossible task. But nobody could prove it was impossible, only that nobody had managed it. Now here is the secret connection. The numbers you can construct with a compass and straightage, starting from a unit length, are a very restricted set. You can add, subtract, multiply, divide, and take square roots, and that is all. Every number you can build with those tools is algebraic. It answers to an equation. So if you could square the circle, you would be constructing a length involving pi, which would force pi to be algebraic. But Lindemann had just proven pi is transcendental. It is not algebraic. It cannot be constructed. Therefore, the circle cannot be squared, not because we are not clever enough, but because the universe of constructible numbers simply does not contain the number you would need. A 2,000-year-old problem was not solved. It was dissolved. It was shown to have been impossible the entire time. Impossible in principle. Impossible forever. and the proof of that impossibility ran straight through the transcendence of pi. I find the human aftermath of this almost as interesting as the mathematics, because it contains a small injustice that historians still argue about. Hermite built the engine. He proved he transcendental, he developed the entire method, and he was the one with the genius to see how it all worked. Lindemann took that engine and drove it the last mile to pi, which required a real and clever insight, but in the view of some, far less than what Hermite had done. And it was Lindemann who got the immortality. Squaring the circle was the famous problem, so the man who killed it became the famous name. There are mathematicians who have written, with some bitterness on Hermite's behalf, that Lindemann was clearly the lesser mathematician who happened to be standing in the right place to grab a famous result that Hermite had done the hard work to make possible. Whether that is fair to Lindemann is genuinely debatable, and I lean toward thinking it is a little unfair, because seeing the last step is not nothing, but the pattern it shows is one we have already seen and are going to see again and again. The person who does the deep work and the person who gets the credit are often not the same person, and the gap between them is rarely about the quality of the mathematics. There is one more piece of the pi story that I cannot leave out, because it is the exact misunderstanding I asked you to drop at the very beginning, and now I can show you why it matters. People had known pi was irrational since 1761, when Johann Lambert proved it, so for over 100 years before Lindemann, everyone knew pi's decimals went on forever without repeating. And here is the trap. If you think irrational is the end of the road, if you think the wildest a number can be is to have non-repeating decimals, then Lambert's proof should have settled the squaring of the circle right there in 1761. But it did not, and it could not, and the reason is the entire point. Irrationality is not enough to forbid construction. The square root of 2 is irrational, and you can absolutely construct it with a compass and straightedge. It is just the diagonal of a unit square. Irrational numbers can still be algebraic, still answer to equations, still be constructible. To prove the circle cannot be squared, you needed something far stronger than irrationality. You needed transcendence. You needed to prove that pi does not just have messy decimals, but answers to no equation at all. And that is why the problem stayed open for another 121 years after Lambert, until Lindemann, building on Hermite, supplied the stronger thing. The distance between irrational and transcendental is not a technicality. It is the distance between a number that is merely untidy and a number that is genuinely lawless. And almost everyone walks around their whole life thinking those two words mean the same thing. By 1882, we finally had it. Two of the most important numbers in all of mathematics, E and pi, proven transcendental, proven to be genuine members of Cantor's ocean. Not freaks built by hand, but natural constants pulled from the deep structure of reality and shown to be unnameable by algebra. You would think this is the moment the floodgates open. You would think that now, with the method established and the two biggest fish landed, mathematicians would go down the list of important constants one by one and sort them all into algebraic or transcendental. And within a few decades we would have a clean census of the number line. That is what should have happened. It is not what happened. What happened instead is that the progress almost completely stopped, and the gap between what Cantor proved about all numbers and what we can prove about any particular number became a chasm that we are still standing at the edge of right now. And that chasm is the second foreshadow I owe you, so let me make it explicit before we go further down. Here is the thing I need you to start feeling now, because it is going to become the whole story by the end. Cantor proved that almost every number is transcendental. Probability 1. Certainty. The unnameable numbers are not just most of the line, they are effectively all of it. And yet, in the nearly 200 years since Liouville opened the door, the total number of naturally occurring constants that human beings have actually managed to prove transcendental is a list you could write on a single page. Pi, E, A, handful of others we are about to meet. That is roughly it. We have proven the ocean exists, we have proven the ocean is everything, and we have personally named and verified maybe a dozen drops of it, and several of those we had to build ourselves. The gap is not closing with time, the gap is structural. We are about to see that for the overwhelming majority of specific numbers, including numbers that show up constantly in real mathematics, we cannot prove they are transcendental, we cannot prove they are not. And for some of them we cannot even prove the much weaker statement that they are irrational. The silence is not temporary. It runs all the way down. And the deepest version of that silence, the one waiting at the bottom, is not about any particular number at all. It is about whether the question even has an answer. Let me show you the rest of the named list first, the few drops we did manage to pull out, because they came from one more burst of genius, and then the burst ended. In 1900, at the Great International Congress of Mathematicians in Paris, David Hilbert stood up and laid out a list of 23 problems that he believed would shape the next century of mathematics, and the 7th problem on that list was about transcendence. He asked whether a number like 2 raised to the power of the square root of 2 is transcendental. More generally, whether an algebraic number raised to an irrational algebraic power is always transcendental. And Hilbert, who had a good sense for these things, reportedly believed this problem was so hard that it would not be solved in his lifetime. That it was harder than proving the Riemann hypothesis, harder than Fermat's last theorem. He thought it would outlive him by generations. It was solved in 1934, well within his lifetime, by 2 men working independently, the Soviet mathematician Alexander Gelfond and the German mathematician Theodor Schneider, who was a graduate student at the time and proved it as part of his doctoral thesis. The result is now called the Gelfond-Schneider theorem, and it is the reason we can say with certainty that 2 to the power of the square root of 2 is transcendental, and that the number e raised to the power of pi, a strange and beautiful constant equal to about 23.14, is transcendental. That number, e to the pi, is sometimes called Gelfond's constant, and it is one of the very few cases where we know the constant is lawless. There is a wonderful asymmetry here that tells you how brutal this subject is, because we can prove e to the pi is transcendental, but pi to the e, which looks almost identical, just the exponent and base swapped, is to this day not known to be transcendental, is not even known to be irrational. Swap 2 symbols and you fall straight off the edge of human knowledge. That, essentially, is the list. The drops we have pulled from the ocean and verified. Liouville's manufactured constant from 1844, E from Hermite in 1873, pi from Lindemann in 1882, 2 to the square root of 2 and e to the pi from Gelfond and Schneider in 1934. A natural logarithm here, a sine of a rational angle there, a few more constructed examples like Champernowne's number, which a Cambridge undergraduate named David Champernowne built in 1933 by just stringing all the whole numbers together after a decimal point. 0.123456789101112, and which was later proven transcendental by Kurt Mahler. Add it all up and you have a list of named, verified, transcendental numbers that, against an uncountable ocean that fills 100% of the line, is so small it rounds to nothing. It does round to nothing. It has measure 0. The set of transcendental numbers we have actually named is mathematically the same size as the set of numbers we can name at all, which is to say 0% of what is out there. And now I want to take you into the gap itself, into the specific numbers we cannot reach. Because abstract talk about measure zero is one thing and standing in front of an actual, simple, important number that we cannot crack is another, and the second one is where the vertigo lives. I want to introduce you to a number called the Euler-Mascheroni constant, written with the Greek letter gamma, and I want you to understand that this is not some exotic construction. Gamma shows up constantly. It appears in number theory, in calculus, in the study of how prime numbers thin out, in physics, in the analysis of algorithms. It is roughly 0.5772. It is defined by something almost embarrassingly natural. Take the harmonic series, 1 plus 1/2 plus 1/3 plus 1/4 and so on, which grows without bound but very slowly, roughly like the natural logarithm. Gamma is the gap, the constant difference, between that sum and the logarithm, in the limit. It is one of the most important constants in mathematics. It has been studied for over 250 years. We have computed it to trillions of decimal places. And we cannot prove it is irrational. Sit with that. We do not know, in the year this is being made, whether the Euler-Mascheroni constant is a simple fraction or not. Not transcendental, that is far out of reach. We cannot even establish the baby step, the thing we have known about pi since 1761 and about the square root of 2 since the ancient Greeks, that it cannot be written as one whole number over another. It might, for all anyone can prove, be some fraction with an enormous denominator. We strongly believe it is irrational and almost certainly transcendental. Everyone believes that. But belief is not proof, and the proof does not exist. The best anyone has managed is a kind of grudging boundary, a result showing that if gamma is a fraction, then its denominator has to be astronomically large, a number with more than 240,000 digits. That is the state of the art. Not, it is irrational. Just, if it somehow is a fraction, the fraction is monstrous. There is a story, probably apocryphal but too good not to mention, that the great English mathematician G.H. Hardy offered to give up his prestigious chair at Oxford to anyone who could prove gamma is irrational. Nobody collected. The chair was safe. And gamma is not alone. There is Catalan's constant, another natural object, roughly 0.916. That appears all over combinatorics and analysis, and its irrationality is also unproven, still open, still beyond us. There is Apéry's constant, the sum of 1 over every whole number cubed, 1 plus 1/8 plus 1/27 and so on, which equals about 1.202. In 1978, a French mathematician named Roger Apéry, who was in his 60s, an age at which mathematicians are usually considered finished, stunned the entire field by proving that this number is irrational. The proof was so strange and so full of mysterious steps that the audience at his first lecture largely did not believe him, and it took months of work by others to confirm that this old man, working alone and against the assumption that he was past it, was completely right. But here is the cruelty even in that triumph. Apéry proved it is irrational. He did not prove it is transcendental. And to this day, decades later, nobody has. We know it is not a fraction. We do not know if it answers to an equation. It sits in the narrow band between irrational and transcendental, half classified, and there it remains. I could go on, and the list does go on, and it includes some of the most basic combinations you could imagine. Take pi plus e. Just add the two most famous transcendental numbers together. Is the result transcendental? Is it even irrational? Nobody knows. Take pi times e. Same answer. Nobody knows. We have proven both pi and e are individually lawless. Two of the only natural numbers we have ever managed to prove that about, and we cannot prove that their sum is even irrational. There is exactly one crumb of comfort available, and it is the kind of comfort that makes things worse. Using a simple argument, you can prove that at least one of the two numbers, pi plus e or pi times e, must be transcendental. They cannot both be tame. But the proof cannot tell you which one. It guarantees the lawlessness is there, in one of them or both, and then it shrugs and refuses to say where. We can prove the monster is in one of the two rooms, and we cannot prove which room. This is the abdication, and I want to name it plainly because it is the emotional centre of the whole subject. We are not talking about exotic frontier mathematics here. Gamma, Catalan's constant, pi plus e, these are not strange objects from the edge of research. They are some of the first numbers you would write down if you sat for an afternoon, combining the constants you already know. They are, by the standards of this field, simple, and the entire combined effort of the mathematical species. Over centuries, with computers, with the diagonal argument, with everything Cantor and Hermite and Lindemann and Gelfand built, cannot tell you whether the Euler-Mascheroni constant is a fraction. The people who are supposed to understand numbers, who built the entire towering edifice that proves almost all numbers, are transcendental, cannot prove it about the specific numbers sitting in front of them, not because they are lazy, because the tools do not reach. Cantor handed us a proof that the ocean is everything, and then the ocean turned out to be made of water we cannot touch. Assume that having proven it lawless, having now computed it to something like 100 trillion decimal places with modern machines, we would at least understand the basic statistical texture of its digits. There is a simple property a number can have, called being normal, which means, roughly, that its digits are perfectly democratic. Every digit from 0 to 9 appears equally often in the long run. Every pair of digits appears equally often. Every block of any length shows up with exactly the frequency you would expect from pure chance. A normal number is one whose digits show no statistical bias of any kind, no favourite, no hidden lean. And the question is whether pi is normal. We have its digits by the hundreds of billions. We have run every test anyone has thought of. They look completely, flawlessly uniform, exactly as if they had been generated by rolling a fair 10-sided die forever. And we cannot prove it. Not for pi, not for e, not for the square root of 2, not for any naturally occurring constant. The statement that pi is normal, that its digits do not secretly favour some number over another, a statement that every shred of evidence screams is true, has never been proven, and nobody has any real idea how to prove it. This deserves a moment, because it is its own small abdication nested inside the larger one. We named pi. We proved the deep hard thing, that it transcends all of algebra, and we cannot prove the shallow obvious looking thing, that its digits do not lean towards sevens. That inversion, where the famous monstrous problem falls and the simple looking one stands untouched, runs all through this subject, and it should make you distrust your instinct about what is hard and what is easy in mathematics. The numbers we can name are not numbers we have mastered. They are numbers we have managed to point at. Pointing is not understanding. We have a name for pi, and a proof that it transcends algebra, and 100 trillion of its digits sitting on a drive somewhere, and we still cannot answer a question about it that you could pose to a child. The handful of drops we pulled out of the ocean, we cannot even fully read. I want to say something plainly here that usually does not get said, because the polite version of this story treats the gap as a neutral fact, a frontier we are slowly pushing back, and I do not think that is honest. The honesty is this. We built an entire cathedral of mathematics on top of the real numbers. Calculus, analysis, the foundations of physics, all of it assumes the continuum. assumes the line is there in its full uncountable completeness, every point present and accounted for. And we did that knowing, since Cantor, that we can name almost none of the points we are assuming. We treat the line as a finished, available object, we work with it every single day, and almost every element of it is something we have proven we can never reach. There is something a little dishonest in how comfortably we use a thing we know is almost entirely beyond us, and that discomfort, I think, is part of why the deeper facts get quietly left out of the way the subject is taught. It is easier to draw the tick marks and the few familiar numbers and let the student assume that is what is there. To tell a 14-year-old that the line they are graphing on is built almost entirely from numbers that no one will ever name would be true, and it would be unsettling, and it would not fit on the test, so it gets left out, and the student grows up believing the postage stamp is the ocean, the same way you did, the same way I did. And the people who know better mostly do not dwell on it either, and not because they are hiding anything. The proofs are right there in every textbook for anyone who reads to the end of the chapter. It is something quieter and more human than a conspiracy. It is that the implication is uncomfortable, and the work goes on perfectly well without staring at it, so almost nobody stares at it. The same instinct that made Kronecker call Cantor a corrupter of youth rather than check his proof. The same instinct that let the mathematical world receive Liouville's first Transcendental with a polite nod and then forget it for 30 years, is still running. It is the instinct to absorb the technique and look away from the meaning. We took Cantor's diagonal argument and turned it into a homework exercise, a clever move that first-year students learn to reproduce on an exam, and we stopped feeling the thing it actually proves, which is that the reality we model with the Continuum is overwhelmingly composed of objects we have demonstrated with certainty that we will never access. The trick got domesticated. The thing the trick proves did not get any less true. It just got filed under solved and shelved, and a thing that is shelved stops being looked at, and a thing that stops being looked at might as well. For a species that would rather be comfortable not be true at all. Now, you might be tempted at this point to make peace with the situation, to tell yourself, all right, the transcendental numbers are almost everything, and we can only name a few, but naming is a human limitation, a matter of effort and cleverness. Give us enough centuries and enough brilliance, and we will name more of them. The gap is large, but it is the kind of gap that knowledge slowly fills. I am about to take that comfort away from you, and I am going to take it away in a specific and permanent direction, because the next man in this story did not prove that we have not yet named most numbers. He proved that most numbers cannot be reached by any process whatsoever, that there is no method, no algorithm, no machine, no procedure that will ever produce them, and that this is not a limitation of our cleverness, but a hard wall built into the structure of computation itself. And to set it up, I have to correct one more thing you probably believe about transcendental numbers, because it is the bridge to the bottom. You probably assume that a lawless number, a transcendental, must have random-looking, patternless, chaotic digits. That transcendence means disorder. It is a natural assumption, and it is false, and the falseness of it is the doorway to everything that follows. Go back to Liouville's constant, the very first transcendental anyone ever named. Its digits are not random at all. They are a 1 in every factorial position, and zeros everywhere else. The most orderly, predictable, describable pattern imaginable. You could write a child a rule for generating its digits in one sentence. It is perfectly transcendental and perfectly patterned. Same with Champernowne's number, 0.1234567891091011, just the counting numbers glued together, transcendental and yet so orderly that a kindergartner could continue it forever. So transcendence is not randomness. Being lawless in the algebraic sense, having no equation, has nothing to do with whether your digits follow a describable rule. And that distinction, the difference between a number with no equation and a number with no describable rule at all, is exactly the cliff edge we are about to walk off. Because Liouville's constant has no equation, but it does have a rule. The question that breaks everything is, what about the numbers that have no rule either? The man who asked that question and answered it was Alan Turing, and he answered it in 1936 when he was 24 years old, in a paper with one of the most consequential titles in the history of thought, Uncomputable Numbers, with an application to the Entscheidungsproblem. If you have heard of Turing at all, it is probably for two things: breaking the German Enigma codes during the Second World War and being persecuted to death by the British state for being gay. And we will get to both, because they are part of this. But the paper that made him immortal, the one he wrote before the war, was about exactly our question. It was about which numbers a machine can produce. Turing did something that, in retrospect, was so clarifying that it created an entire field. He asked, what does it actually mean to calculate a number? And to answer it, he invented, on paper, an idealized machine. A thing we now call a Turing machine, which is the abstract mathematical skeleton of every computer that has ever been built, including the one rendering these words. It is a very simple thing in principle: a strip of tape, a head that can read and write symbols on the tape and move left or right, and a finite list of rules telling it what to do. That is it. And Turing's astonishing claim, which has held up for 90 years and underlies all of computer science, is that anything that can be calculated by any definite step-by-step procedure at all can be calculated by one of these machines. Any algorithm, any computation, any mechanical process for producing an answer is captured by some Turing machine. The machine is the mathematical definition of what computation is. So Turing defined a computable number as a real number whose digits can be churned out by one of these machines. You feed it the rules, you let it run, and it spits out the decimal expansion, digit after digit, as long as you let it go. Pi is computable. There are machines, there are actual programs running on actual computers right now that generate pi's digits indefinitely. E is computable. The square root of 2 is computable. Liouville's constant is computable. You just print a 1 at the factorial positions. Champernoun's number is computable. Every famous constant you have ever heard of, Gamma and Catalan's constant and Apéry's constant included, every single one is computable. They have rules. A machine can produce them. And here is where Turing brings back the weapon, the diagonal argument, the exact move Cantor used in 1891, and turns it against computation itself. How many Turing machines are there? Each one is just a finite list of rules, a finite set of instructions written in a finite alphabet, and you can take any such finite list and write it out as a single finite string of symbols. And you can put all possible finite strings in order, short ones first, then longer ones alphabetically within each length, the way a dictionary is ordered. Which means the Turing machines can be listed. There is a first one, a second one, a billionth one, every possible program appearing somewhere on a single endless list. The programs are countable. And since every computable number comes from some program, the computable numbers are countable too. You can list every number that any machine could ever produce. You already know what happens next, because you have seen this exact move before. If the computable numbers can be listed, then Cantor's diagonal argument applies to them with no modification at all. Take the list of every computable number between 0 and 1. Build a new number that differs from the first computable number in its first digit, from the second in its second digit, from the nth in its nth digit, straight down the diagonal. The number you build cannot be anywhere on the list. it differs from every computable number in at least one place, which means the number you have just built is not computable. No machine can produce it. There is no algorithm, no program, no procedure that will ever output its digits. Because if there were, it would be on the list, and it differs from everything on the list. And just as before, this is not one weird exception. The computable numbers are countable, so they have measure 0. So they occupy 0% of the line, so the dart thrown at the line between 0 and 1 lands with probability 1 on a number that no machine can ever compute. Not has not yet computed. Cannot compute. Will never compute. Not in this universe or any other, not with any technology, not given any amount of time. I need you to feel the size of what just happened, because it is bigger than the transcendental result, and it contains it. Every transcendental number we have ever named, pi and e and the rest, is computable. They are the nameable ones precisely because they have rules a machine can follow. So the entire ocean of named transcendentals, the thing that already dwarfs the algebraic numbers, is itself just a measure 0 sliver inside a vastly larger ocean of numbers that no machine can produce at all. There is the line you were taught, the rationals and a few roots. Inside the unnameable vastness around it sit the transcendentals. And inside the transcendentals, the computable ones, the ones with rules, pi and e and Liouville's constant and every other number any human or machine will ever calculate, are themselves a measure 0 accident floating on an ocean of numbers that have no rules at all. The dart does not just land on a number with no name. It lands on a number that no possible machine could ever name even if it tried forever. We have gone one floor deeper, and the floor we were standing on, the floor of nameable transcendentals that already felt like almost nothing, turns out to have been almost nothing inside something far larger. And Turing, having proven this, having shown that almost every number is uncomputable, did the thing that makes him Turing. He used the same machinery to prove that there are questions no computer can ever answer, that there are mathematical truths no algorithm can ever decide, the famous halting problem and the undecidability of the Entscheidungsproblem, which is a German word for the decision problem, the dream of a mechanical procedure that could determine the truth of any mathematical statement. Turing killed that dream in the same paper with the same diagonal blade, and in doing so he did not just describe computers. He drew, forever, the boundary of what computation can and cannot do, and he showed that the cannot is the overwhelming majority, the realm of the computable, the realm where every machine and every program and all of digital reality lives, is a thin bright line drawn across an infinite dark page. The biography here is almost unbearable given what the man proved, and the parallel is so exact it feels arranged. Turing spent the war at Bletchley Park breaking German naval codes, work that saved an enormous number of lives and helped win the war, and was kept secret for decades, so that he received almost none of the public credit during his lifetime. In 1952 he was convicted of gross indecency, the legal term Britain used for homosexual acts, after he reported a burglary and, in the course of it, admitted to a relationship with another man. He was given a choice between prison and chemical castration, a course of synthetic estrogen injections meant to suppress his sexuality, and he chose the injections so that he could keep working. His security clearance was revoked. The state that he had served, the state whose existence he had helped preserve, took the man who had defined the limits of computation and tried to chemically rewrite the computation running in his own body. On the 8th of June, 1954, he was found dead in his home. He was 41 years old. The cause was cyanide poisoning, and beside his bed was a partly eaten apple, which was never tested for cyanide, but which has fed the lasting image of his death. an image his biographer noted carries an echo of the poisoned apple from Snow White, a film Turing had loved. The inquest ruled suicide. Some who have studied the evidence carefully think it may have been an accident, an inhalation of cyanide fumes from an experiment he was running. We do not know for certain, and we never will, which is its own quiet horror, given that this is a man who spent his life on the question of what can and cannot be determined. The man who proved that almost every number is permanently beyond the reach of any machine was himself subjected to a machine. The apparatus of a state that decided his nature was a problem to be computed away. He did not receive a formal apology from the British government until 2009, and a royal pardon until 2013, decades after his death, the now familiar pattern. Vindication arriving long after the person who needed it is gone, and the work he did, the boundary he drew, sits underneath every device you own and every line of code that runs the world, while the numbers he showed are unreachable continue to be unreachable, an infinity of them, all around the thin lit edge where computation lives. But I told you we were going further than the uncomputable, and we are, because there is one more specific number I have to show you before we go past specific numbers entirely, and it is the strangest object in this entire story. Remember that Turing proved most numbers are uncomputable, but the way he proved it, with the diagonal, gives you a freak again, a number defined relative to a list. The same flavour of manufactured monster as Liouville's constant and Cantor's diagonal number. The natural question, the one that took another 40 years to answer well, is whether there is a specific, definable, natural, uncomputable number, the way pi and e are specific, natural, computable ones. A number you can point to and describe completely that is nonetheless impossible to calculate. And the answer is yes, and the man who found it is named Gregory Chaitin, and the number is called Chaitin's constant, written with the Greek letter omega. Here is what omega is, and it is worth slowing down for because it is one of the most remarkable definitions in mathematics. Imagine feeding random programs into a universal computer. Some programs, when you run them, eventually stop and give an answer. Others run forever, caught in loops, never halting. Chaitin's omega is roughly the probability that a randomly chosen program will eventually halt rather than running forever. It is a single specific number between 0 and 1. It has a completely precise definition, which I just gave you. It is not vague. It is a particular real number, as definite as pi. And it is uncomputable, provably, absolutely. No algorithm can produce its digits. And the reason it is uncomputable is breathtaking, because knowing the digits of omega would let you solve Turing's halting problem, would let you determine, for any program, whether it eventually stops. And since Turing proved that is impossible, omega's digits must be impossible to compute. Omega is a number whose every digit encodes the answer to an unanswerable question. And omega is not just uncomputable, it is transcendental, of course, since all computable numbers include the algebraic ones, and omega is not even computable. But it is more than transcendental. Its digits are, in the precise technical sense, perfectly random, algorithmically random. Incompressible, there is no rule, no pattern, no shortcut, no description shorter than the digits themselves that could generate them. Remember the distinction I drew earlier between Liouville's constant, which is transcendental but has a simple describable rule, and the idea of a number with no rule at all. Omega is the number with no rule. Its digits are maximally lawless, not just without an equation, but without any pattern of any kind, a sequence of pure information with no internal structure to exploit. If you somehow learned the first 10,000 digits of omega, they would help you not at all in guessing the 10,001st. It It is the cleanest example mathematics has of irreducible randomness, a specific, definable number that is nonetheless made of pure unpredictability all the way down. I should be honest about a subtlety here, because this story is too important to oversimplify, and because the honest version is more interesting than the myth. Omega is not quite a single number. It depends on the choice of universal computer you start with, so there is really a family of related omega constants, one for each choice of machine. And there are mathematicians who argue that the way people talk about omega as a definite number whose digits exist but are unknowable smuggles in philosophical assumptions about what it means for digits to exist that we should be more careful about. These are real debates, and I am not going to pretend they are settled. But the core fact survives all of them. There exist specific, completely definable real numbers that no machine can compute, and whose digits carry no extractable pattern. Numbers that are at once perfectly specified and perfectly unreachable. Omega is the proof that the unreachable is not always vague. Sometimes you can describe a thing precisely and still never touch it. We have now descended through 2 floors, the transcendental numbers, almost all of the line, of which we can name only a handful, and inside the nameable ones, the computable numbers, themselves a measure zero sliver, surrounded by an even vaster ocean of numbers no machine can ever produce. And you might think, surely that is the bottom. Surely uncomputable is as unreachable as a number can get. If no machine can produce it, what worse fate is there for a number than that? And here is where I have to take you to the floor below the floor, the one that took me longest to understand, and that I am still, if I am honest, not fully comfortable with, because it stops being about machines and starts being about language itself, about whether a number can be described at all, by any means, in any words, ever, because it turns out that computability, as unreachable as it sounds, is not the bottom. There is a level of unreachability below it, and at that level the numbers cannot even be talked about. Think about what it takes to specify a number. Not to compute it, just to single it out, to pick it from the line and say, that one. The number I mean is this one and no other. You can do it with a name, like pi. You can do it with a formula, the ratio of a circle's circumference to its diameter. You can do it with a description in plain words, the smallest positive number whose square is 2. You can do it with a computer program. You can do it with a definition in the formal language of mathematics, a precise logical sentence that picks out one and only one real number. All of these are ways of reaching a number through language, through a finite string of symbols. And every one of them, every name, every formula, every description, every program, every logical definition, is a finite sequence of characters drawn from some finite alphabet. And now you know exactly what is about to happen, because the move is always the same. How many finite strings of symbols are there? Take any fixed alphabet, the letters and digits and mathematical symbols, anything you like, as long as it is finite. The strings of length 1, there are finitely many. The strings of length 2, finitely many. And so on. So the set of all possible finite descriptions, every sentence that could ever be written or spoken, every formula, every definition, every program, in every human language and every mathematical notation that exists or could exist, is countable. You can list them, shortest first, the way a library could in principle shelve every possible book. The descriptions are countable, and the real numbers are not, which means, by the same brutal arithmetic we have used at every level, that almost every real number has no description of any kind, not no equation, not no algorithm, no description, no finite string of symbols in any language that picks it out. The number is real, it is on the line, your dart can land on it, and there is no sentence, no formula, no name, no definition, no program, Nothing you could ever write or say that would distinguish it from all the others. It cannot be referred to. It cannot be specified. It is, in the most complete sense of the word, ineffable. This is the floor below computability, and you can see why it is lower. To compute a number, you need an algorithm, which is one particular kind of finite description. But there are finite descriptions that are not algorithms, descriptions that specify a number without giving you a way to calculate it, the way the phrase "the probability that a random program halts" specifies omega without computing it, so the describable numbers are a larger set than the computable ones. And yet, even the describable numbers, this larger and more generous set that includes every name and formula and definition humanity could ever produce, is still only countable, still measure zero, still 0% of the line. Throw the dart. With probability 1, it lands on a number that you cannot name, cannot compute, cannot define, cannot describe, cannot single out by any finite means whatsoever. Not because no one has bothered, but because there are not enough possible descriptions to go round. There are uncountably many numbers and only countably many things we could ever say. The numbers outnumber the sentences so completely that almost every number is condemned to permanent, total, structural silence. It will never be spoken because there are no words left to speak it with. That is the math T argument, so called because it is the kind of thing mathematicians mutter to each other over tea, and when I first encountered it, it genuinely unsettled me in a way that few things in mathematics have, because it seems to prove that the overwhelming majority of the numbers making up the line, making up the continuum that we use to model space and time and everything. Continuous in physics are not just unknown, but unknowable, unsayable, forever beyond the reach of any mind or language. And I want to keep faith with you here, because this is exactly the kind of claim that gets overstated in popular accounts, and the real version has a twist in it that is stranger than the clean version. And the twist is the most intellectually honest and most interesting part of the whole subject, so I am not going to skip it the way most tellings do. The twist is this. The argument I just gave you sounds airtight, and as an informal piece of reasoning it is compelling, but when you try to make it a rigorous theorem inside the formal foundations of mathematics, it springs a leak. And the leak is profound. The problem is the word definable. To run the argument rigorously, you need to talk about the set of all definable real numbers, and then show it is countable, and then conclude the rest are undefinable. But it turns out that the notion of definability cannot, in general, be defined inside the very system you are working in. There is a famous, very old warning sign here, called Richard's paradox, discovered by the French mathematician Jules Richard in 1905. It goes roughly like this. Consider all the real numbers that can be defined in English in a finite number of words. That set is countable, so list them. Now use the diagonal argument on that list to define a new number that differs from the nth listed number in its nth digit. But wait, I just defined that new number, in English, in finitely many words, in the very sentence you are reading, so it should be on the list. But by construction it differs from everything on the list. Contradiction. The number is definable and undefinable at the same time. Richard's paradox is not a flaw in mathematics. It is a flaw in the naive idea that you can talk about definability from inside the system using the system's own language. The resolution, worked out over the following decades and connected to some of the deepest results in logic, is that there is no consistent way for a formal system to define its own notion of definability. The phrase "the set of all definable real numbers," which the math T argument leans on, does not actually pick out a well-defined set inside standard mathematics, and the consequences of this are genuinely vertiginous. In 2013, the logician Joel David Hamkins, together with two colleagues, proved something that sounds impossible given everything I have just told you. They proved that there exist legitimate models of set theory, complete consistent universes of mathematics obeying all the standard axioms, in which every single real number is definable. Every one. No undefinable numbers at all. A whole mathematical universe in which the math-T argument is simply false, where every real has a name. How is that possible when the counting argument seemed so ironclad? Because in such a universe, the map that would pair up each definition with the number it defines cannot itself be constructed inside that universe. The universe contains all the definitions and all the numbers, and a perfect pairing between them, but it cannot see its own pairing, cannot form it into a single object it can reason about, and so it cannot run the diagonal argument to derive a contradiction. From the inside, every number has a name, and the universe cannot prove otherwise. Because the very act of counting the names is something it is unable to perform on itself. The undefinable numbers are undefinable in a way so total that whether they even exist depends on where you are standing, on which model of mathematics you inhabit, and there is no absolute vantage point from which to settle it. I told you I am still not fully comfortable with this, and that is the honest truth. Because what it means is that the deepest level of unreachability is not even a fixed fact about the line. It is relative. It shifts depending on the foundations you choose. The clean horror story that almost all numbers are provably unnameable is not quite a theorem. The real situation is subtler, and to me, worse. Because it means the question of how much of the number line is even in principle accessible to description does not have a single stable answer. It depends on which universe of sets you are living in, and we have no way to know which one that is, and there may be no fact of the matter about which one is the real one. We have descended so far that the floor itself has stopped being solid, and that is the perfect place to arrive at the bottom, because the bottom of this entire staircase is precisely the discovery that the foundations of mathematics do not determine the answers to the questions we most want to ask about the line, and the cleanest example of that, the one that closes the circle all the way back to Cantor, is the question he died on. I asked you, a long way back now, to hold on to the continuum hypothesis. The question of whether there is any size of infinity strictly between the countable whole numbers and the uncountable reals. Cantor believed the answer was no, that the reals are the very next infinity after the integers with nothing in between, and he spent the back half of his life trying and failing to prove it. And he died in the sanatorium believing it was a question that God knew the answer to, and that he had simply failed to find. It became the first problem on Hilbert's famous list in 1900, the single most important open question in set theory, the thing the best minds of the 20th century threw themselves at. And here is what they found, in 2 stages, separated by 25 years, and it is the most disorienting resolution to a mathematical question that I know of. In 1940, Kurt Godel, the same Godel who had already shattered mathematics once with his incompleteness theorems, proved that you cannot disprove the continuum hypothesis using the standard axioms of mathematics. The axioms called Zermelo-Fraenkel set theory with choice, the foundations on which essentially all of modern mathematics is built. He showed it is consistent with those axioms. You will never derive a contradiction by assuming Cantor was right. So far, that sounds like progress toward Cantor. But then, in 1963, a young American mathematician named Paul Cohen, working at Stanford, invented an entirely new technique, a method called forcing, which let him build models of set theory to order, and using it he proved the other half. He proved that you cannot prove the continuum hypothesis either. He built a universe of mathematics, obeying every standard axiom, in which there is a size of infinity between the integers and the reals. Cantor's hypothesis is false in that universe, and the universe is perfectly consistent. Put the 2 halves together, and you get the thing that I think is the genuine bottom of this entire descent. The continuum hypothesis can be neither proved nor disproved from the standard foundations of mathematics. It is independent of them. The axioms that underlie all of mathematics, the rules we trust to settle every question, simply do not determine whether there is an infinity between the integers and the reals. The question is not hard. It is not unsolved in the way that a difficult open problem is unsolved, waiting for a clever enough person. It is undecidable. The foundations are silent. You can add an axiom that makes it true, or an axiom that makes it false, and either way you get a consistent mathematics, and there is no internal reason to prefer one over the other. The number of real numbers, the size of the continuum, the answer to the simple question how many points are on the line, is not pinned down by mathematics. It can be one thing or another, and the foundations do not care. Cohen won the Fields Medal for this in 1966, the only Fields Medal ever awarded for work in mathematical logic, and the technique he invented, forcing, became one of the central tools of modern set theory. But I want you to sit with what it did to Cantor's question, because the cruelty of it is almost too neat. Cantor spent his life believing the continuum hypothesis had an answer, that God knew it, that the failure to find it was his failure. He died in an institution, his own mind increasingly unreachable, convinced he had fallen short of a truth that was out there waiting, and the resolution, when it finally came, decades after his death, was not that the answer was yes, the thing he believed, and not that the answer was no, the thing he feared. The resolution was that there is no answer. The question he poured his life into is not answerable, not by him, not by anyone, not by any amount of genius, because the foundations of mathematics themselves do not contain the answer. He thought only God could decide it. It turned out that nothing can decide it. The silence he heard was not the silence of his own inadequacy. It was the silence of the thing itself. There was never going to be an answer, and he spent his life, and arguably his sanity, listening for one. I have kept this inside mathematics so far, and I have done that on purpose, because the mathematics is solid ground and I wanted you standing on solid ground when I asked the next question, which is not solid at all, and which is the reason this story matters beyond the chalkboard. The number line is not just an abstraction that mathematicians play with. It is the thing physics is built out of. When a physicist writes down the position of a particle, the strength of a field, the curvature of space-time, the value of a constant, they write down a real number. The entire mathematical machinery of physics, from Newton to Einstein to quantum field theory, assumes that the quantities describing the world live on the continuum. That same line we have just spent 2 hours discovering is almost entirely made of numbers we can never name, never compute, never even describe. And so the question that has been crouching underneath this whole story finally stands up. If reality is described by real numbers, and almost every real number is unreachable, then what does that say about reality? I want to be very careful here, more careful than this kind of story usually is when it reaches this point. Because this is exactly where a fascinating true thing can tip over into nonsense, and I respect you too much to do that. Let me separate cleanly what we know from what we are guessing, because the boundary between them is itself part of the unsettling thing. Here is what we know. The fundamental constants of physics, the numbers that set the strength of the forces and the masses of the particles, are measured, not derived. We do not have a theory that tells us what they must be. We go out and measure them. Take the fine structure constant, the number that sets the strength of the electromagnetic force, roughly 1/137. It is one of the most important numbers in all of physics, and we have measured it to extraordinary precision. And we have no idea why it has the value it has. Richard Feynman, who understood it as well as anyone, called it one of the greatest mysteries in physics. a magic number that comes to us with no understanding, and he wrote that you might say the hand of God wrote that number, and we do not know how he pushed his pencil. And here is the part that connects directly to everything we have been discussing. Because the constant is something we measure, we only ever know it to finite precision, to some number of decimal places with error bars. We do not know its exact value as a real number. And so the question of whether the fine structure constant, in its true exact value, is rational or algebraic or transcendental or computable or describable, is a question that has no current answer and may have no answer we can ever reach, because we can never measure our way to the exact value, and we have no theory that hands it to us. The number that determines whether atoms can exist sits somewhere on the line, and we cannot say what kind of number it is. That much is established. Now here is where the guessing begins, and I will flag it as guessing the whole way. The deeper question is whether space-time itself, the stage that everything plays out on, is actually a continuum, actually made of these real numbered points with infinite precision between any two of them, or whether it is, at the very smallest scales, something discrete, something grainy, something built out of a finite or countable number of pieces. We do not know. This is one of the genuinely open questions at the frontier of physics, tied up with the unfinished search for a theory of quantum gravity. General relativity treats space-time as a perfect smooth continuum. Quantum mechanics hints, in some readings, that there might be a smallest meaningful length, the Planck length, below which the smooth picture breaks down. Nobody has the final answer. But look at what hangs on it, given everything we now know about the line. If space-time is a true continuum, if physical quantities really do take values across the full real number line with infinite precision, then the overwhelming majority of the actual values realized in the physical world, the exact position of every particle, the exact value of every field at every point, are uncomputable, undefinable, unnameable numbers. They would have to be, because those numbers are almost all of the line, and a continuum drawn at random from the line is overwhelmingly made of them. The universe would be writing itself at every point and every instant in numbers that no equation can summon, no machine can compute, and no language can describe. Reality would be built almost entirely out of the ineffable, and the few clean numbers we can name, the ones in our equations, would be a measure zero scaffolding we have draped over an ocean of values we can never access. The physics we can do would be the postage stamp again, laid over an ocean, mistaking itself for the whole. And if space-time is not a continuum, if it is discrete at the bottom, then the real numbers, the entire continuum, are a fiction, a useful, beautiful, astonishingly effective fiction, but a fiction, an idealization that does not correspond to anything actually in the world, and the line we were taught with its uncountable infinity of unnameable points, would be a structure that exists nowhere except in our heads and our mathematics, describing a smoothness that reality does not actually have. There is a principle in physics, sometimes called the Church-Turing-Deutsch principle, named in part for the physicist David Deutsch, who articulated a version of it in 1985, which holds that every physical process can in principle be simulated by a computing device. And Deutsch himself pointed out the tension that sits at the heart of our whole subject, that the classical physics of the continuum, with its real numbered quantities, cannot actually be simulated by a Turing machine, because a Turing machine can only handle the computable numbers, the measure zero sliver, and not the uncomputable ocean that a true continuum would require. So either the universe does not really use the full continuum, in which case the line is a fiction, or it does, in which case the universe is doing something no possible computer could ever simulate, something that reaches into the uncomputable numbers as casually as you reach for a glass of water. I do not know which of those is true. Nobody does. and I want to resist the temptation, which is strong, to tell you that one of them is obviously right, because the honest situation is that we are standing at the edge of physics looking at a question we cannot currently answer, and both answers are strange beyond comfort. Either reality is built out of numbers we can never name, or the smooth line that has been the backbone of physics for 4 centuries is a beautiful lie about a world that is secretly made of grains. Pick your horror. There is no third door that returns you to the comfortable number line of childhood, the friendly one with the tidy tick marks, because that line never existed. It was always either an ocean of the unnameable or a fiction. We just were not told. And that brings me to the thing I have been circling this entire time, the second foreshadow finally arriving at full strength, because I told you near the beginning that the gap between knowing the transcendental numbers are everything and being able to name even one of them was not a temporary gap. Not a matter of waiting for cleverer people, but something structural, and now you can see exactly how structural it is. It is not one gap. It is a staircase of gaps, each one inside the last. We can name only countably many numbers, and the line is uncountable, so almost every number is unnameable. We can compute only countably many numbers, and almost every number is uncomputable. We can describe only countably many numbers, and almost every number is indescribable. And underneath all of those, at the very bottom, we cannot even decide, from the foundations of mathematics, how many numbers there are, whether there is an infinity hiding between the ones we know. At every single level, the reachable numbers are a measure zero accident, and the unreachable ones are everything. And the same blade, Cantor's diagonal, the one move, cut each of those levels open, one after another, like a knife going down through layers of something that has no flaw. Let me take you back to the dart one final time, because I want to end where we started, and I want you to feel how much heavier it is now. You throw the dart at the line between 0 and 1. It lands. It always lands. It lands on a single, definite point, a real number, and that number is, with probability 1, transcendental, so it has no equation. It is, with probability 1, uncomputable, so no machine could ever produce it. It is, with probability 1, undefinable, so no sentence in any language could ever pick it out. And whether the line it landed on even has a determinate number of points, whether the continuum it belongs to has a size that mathematics can fix, is a question that Godel and Cohen proved has no answer in the foundations we have. You pointed at it. It is right there, under the tip of the dart, as real and definite as any number you have ever known. And you cannot say what it is, no one can say what it is, no machine can find it, no language can hold it. And the framework that is supposed to contain all such numbers cannot even tell you how many of them there are. You are touching it, and it is utterly, permanently, structurally beyond you. That is not a number at the edge of the line. That is the typical number. That is what the line is made of. That is what is under your dart every single time. I think about Cantor more than I expected to when I started reading about all this. I think about the fact that he was a deeply religious man who believed he was glimpsing the structure of the divine, and that the structure he glimpsed turned out to be a tower of infinities whose most basic question, the one he cared about most, was provably unanswerable. He placed God at the top of the tower, beyond all the transfinite numbers, in a region he called the absolute, unreachable and incomprehensible. And the bitter joke that mathematics played on him is that he did not have to look all the way up to find the unreachable and incomprehensible. It was sitting in the line between 0 and 1 the entire time. Almost every point on the most ordinary stretch of the number line is exactly the kind of thing he reserved for God. Unreachable, unnameable, beyond the grasp of any finite mind. The absolute was not at the top of the tower. It was the floor he was standing on. It was everywhere. He spent his life climbing toward an unreachable thing that was already under his feet, and the establishment told him he was diseased for looking, and he died in a room built to hold minds that could no longer be reached, surrounded, though he could not have known it in those terms, by an entire continuum of numbers that could not be reached either. And I think about Liouville, the man who opened the door, the man who spent his evenings rescuing a dead boy's rejected genius from the silence of a drawer, dragging Galois back into the light because he could not stand to see a true thing go unspoken. He of all people opened the door onto a number line that is mostly unspoken things, mostly truths with no names, an uncountable infinity of definite real numbers that will go unspoken forever because there are not enough words in any language, human or otherwise, to speak even a fraction of them. He saved one name from the silence. The line he opened the door to is almost nothing but silence, point after point after point of it, stretching out in both directions, dense beyond counting, and we have managed in all our history to pull a handful of names out of it and hold them up, Pi and E and a few others, the way Liouville held up Galois, while behind each name we managed to save. An uncountable ocean of nameless numbers goes on existing exactly as definitely and exactly as unreachably as it always has. Here is what stays with me, and it is the thing I cannot put down. We did not fail to name these numbers, that is the word everyone reaches for, failure, as though more effort or more genius would close the gap, and it will not, and that is the whole point. The numbers we cannot name are not waiting for us to get better. They are not a frontier we are slowly settling. They are a permanent and overwhelming majority of everything that is on the line, and the line is what we have always believed reality is continuous over, and the situation will be exactly as it is now in 1,000 years and 1,000,000 years, and at the heat death of the universe. The named numbers will still be countable, the line will still be uncountable, the dart will still land every time with perfect certainty on something we can never speak. You live on that line. Every length you have ever measured, every duration, every position in space, if the world is truly continuous, is a point on it, and the overwhelming probability, the certainty in fact, is that almost none of those points have names, that you have spent your whole life moving through and measuring and being made of quantities that are in principle unnameable, uncomputable, indescribable, that the smooth continuous reality you take for granted is woven almost entirely out of numbers that no one will ever be able to say. We proved it was there, starting in 1844. We proved it was almost everything in 1874, and we proved by 1963 that we cannot even count how much of it there is. The proof is finished, the numbers are checked, the line is exactly as full of the unspeakable as it has always been. And somewhere between 0 and 1, right now, there is a number that your dart could land on, that is as real as the number 1. That no person and no machine will ever name or compute or describe, that has been sitting there in perfect definite silence since before there were minds to not name it, and will go on sitting there in silence long after the last mind is gone. It is not hiding, it is not far away, it is closer than the nearest fraction, packed in among uncountably many others exactly like it. Filling the line you were taught was friendly, and it has no name. It will never have a name, and neither, it turns out, will almost everything else.